Okay. So just a quick reminder that all of our materials are copyrighted. You'll all be receiving a copy of these materials in PDF format once the session is done. But before sort of sharing it through any sort of conference, just make sure you get our permission. But you can also feel free to share the materials with your colleagues in the office, though. That's perfectly fine. Okay, so now let's go over to today's learning objectives. So we have three main objectives for today's session. So at the end of this course, we just want all participants to understand these three major concepts. So first and foremost, the key differences between conventional PY method and numerical analysis. So these are the two main methods that are used for deep foundation analysis, each of which has their own very unique set of weaknesses and advantages, and we'll go over those in detail today. Then unique benefits of numerical analysis, as I alluded to previously, and then the application of numerical analysis through case studies on various foundation types. So we actually have a case study submitted to us by one of our clients today from Langen, and we're very excited to share. So we'll go over that in detail near the end of this session. Right, and here's today's sort of table of contents, which is the outline of the presentation. So first is the background of foundations in general. Then we'll go over foundation design methods for single as well as group piles, and then pile raft foundations. So the three main types of pile foundations that you'll be working with. And then numerical analysis for pile foundations, and then a case study for a tower in Dubai. And then last, I'll go over a couple of numerical modeling demonstrations, one with SoilWorks and one with GTS, to conclude the session. Okay, so first, let's talk about the background of foundations. So we'll give you an introduction to pile analysis, the types of foundations or the types of piles that are available, and then also load resistance of deep foundations. Okay, so first, as far as foundations, there are two main types of foundations. There's shallow foundations for smaller structures, usually sort of smaller residential structures, warehouses, anything that is sort of built within a firm foundation and has a sort of very small or relatively small superstructure. Then we have deep foundations for high-rise buildings, large structures, or structures that are built in soils that have sort of looser or less resilient sort of resisting force. And then within shallow foundations, we have footing and mat foundations. So just 2 weeks from now, I'll go more into detail about shallow foundations as well as sort of the different design methodologies that are used for them. So these are all things that you can look forward to in session 3, just going into detail about these different types of shallow foundations. But today's session will focus on deep foundations. So here we have three types of deep foundations: pile foundations, which will be the focus of today's course, and then pier foundations, also known as drill shafts, and then caissons. So once again, this will be the focus, just deep foundations, and in particular piles, because these are the most commonly used. Okay, so as far as just an introduction to numerical analysis, I just want to share a quote from Professor Braha and Das, one of the leaders in pile foundation analysis. And a quote that's really important to sort of understand when doing pile analysis is the following. It says, although numerous investigations, both theoretical and experimental, have been conducted in the past to predict the behavior and the load-bearing capacity of piles, the mechanisms are not yet fully understood and may never be. So just keep in mind that the sort of the understanding of pile foundations, it's always in a state of getting better. There's always, there's professors who are still working on ways to improve upon the methodologies that we're currently using. However, the design of pile foundations has many variables to take into account. So because pile foundations, they're structurally speaking, they're not very complex structures, but their interaction and the soil around them leads to so many uncertainties that behavior is almost always unknown. So something that we discussed, I think, previously was how soil behavior is nonlinear. So it makes it sort of difficult to predict, and it becomes increasingly difficult to predict for deep pile foundations. So each case can be an independent case, and there are still complexities in interaction that engineers are still looking after, and researchers are still going on pile analysis and pile foundations. So something that's really great about these courses is that we'll talk about sort of the latest numerical modeling techniques that are used by engineers to handle pile foundation analysis. So even though there's still variables that are yet unsolved, numerical analysis in particular helps us to do our analysis with much more accuracy and much more confidence than previously. Okay, so now let's talk about when to use deep foundations. So now we know that soil behavior is unknown, but let's see when we must use deep foundations. So I might be repeating this for most of the things you already know, but it may be beneficial for a few of you who are still new to deep foundations. So if you have soft soil near the ground surface and is not able to carry your loads, deep foundations are typically used to create a more stable foundation. Then also, if you have large uplift forces, the same goes for collapsible or expansive soil underneath the surface. So if there's a large amount of or significant amount of uplift forces, pile foundations tend to stabilize the structure much more accurately, or much more efficiently than a shallow foundation. So as you can see, whenever soil is particularly weak or expansive, pile foundations can make the structure that's being built upon these soils much more stable than a shallow foundation. Also, if you have a significant amount of lateral loading, pile foundations are very useful in this respect. So as you can see, the deeper the foundation goes, the more resistance it can provide towards lateral loading. Whereas if you had a shallow foundation, a significant amount of lateral load would cause the foundation to fail. Then also, if you also have large sort of tilting risks, so if you have loads that are being sort of applied at an angle, such as if you had both sort of a combination of lateral loads and axial loads, then pile foundations can more readily resist that sort of force. Then also scour effects. So for example, if you have maybe a bridge foundation being built in a river, and then over time you have a certain amount of scour. So if, let's say the water is going downstream, and you have a significant amount of soil building up upon the foundation. Once again, shallow foundations would not be able to resist that sort of effect as efficiently as a pile foundation. And then if you have a stability risk and you have a foundation, even excavation or near a slope, and you want to secure that. So for example, if there's adjacent structures, if there's a neighboring slope, pile foundations provide much more support and much more safety in that regard. So for example, if you're building a shallow foundation here, because it's located so close to an adjacent structure or an excavation, it's more at risk to fail if it's just a shallow foundation. Okay, then also, this is another case I will be talking about in detail today, particularly heavy load. So if you're working on a large structure, say a high-rise building, or a building that experiences a significant amount of loading, maybe a large industrial plant, then it could require, or typically requires, what's called a pile raft foundation. So the pile raft foundation is a combination of a group of piles and then a large sort of concrete slab that distributes the weight accordingly. So this is particularly useful for larger scale projects, and in particular for numerical modeling, pile raft foundations are done using that method, and we'll discuss that in much greater detail later on in this presentation. So these are just the main sort of project types that would warrant a pile foundation to be used and to be designed. And I'm sure as geotech engineers you're already familiar with all of these, but once again it's just a good review for maybe those of you who are maybe new to the field. Okay, so now let's talk about deep foundations. So what are the different types of deep foundations? So based on the material, we have steel piles, concrete piles, as well as timber piles. Concrete piles in particular are the most commonly used at the moment. Now methods of installation, they can be varying. So we have driven piles, we have board piles, and screwed piles. And also the effective installation, as I mentioned in the terminology, we have displacement, and we have small displacement and non-displacement piles. So these are the classifications of the different types of deep foundation piles. Once again, in the interest of time, I won't go into too much detail, but just keep in mind that these are sort of the options that are available to you. Now let's discuss the load resistance of deep foundations. So in order to understand why deep foundations are preferred at the aforementioned conditions, we must understand that the load transfer mechanism, the load transfer mechanism of the pile. So when we load a pile on the top like we have here, loads are transmitted mainly by two things. So one is the shaft friction along the skin of the pile, as represented by these arrows here, and through the base of the pile near the tip, as represented by these large arrows here. So the pile can be designed to be a shaft or a frictional pile without any bearing resistance, to be on the other hand, or to be, on the other hand, of usually the fully end-bearing pile, or the combination of forces. It depends mainly on the soil conditions, but also on the pile itself, the size of the pile, the length of the pile, and partly on the load as well. So once again, all those variables come into account. So just keep in mind that the type of soil that you're working with, if you're working in several different layers, the kind of resistance that those soil layers could give, that could provide anyway would really greatly determine the type of pile you'd use as far as the diameter, or if you're using a group of piles, how many would be included in the arrangement as well as the arrangement itself. But the main thing to sort of get from this slide is just the basic sort of context of how the piles resist force or provide support. So just keep in mind that these two main things are the base resistance as well as the shaft resistance. So these are the two main forces that account for the resistance or for the stability of a particular pile, in addition to obviously your soil conditions. Okay, so let's have a brief summary of what we just went over. So pile foundation behavior is hard to predict because of the pile-soil interaction. We'll discuss this in detail as well, soil structure interaction, how that comes into play I believe in the next section. So this is one of the complexities that makes it sort of difficult to predict a pile behavior. So in order to really accurately predict it, soil structure interaction needs to be taken into account. Also, unstable soil strata needs deep foundation to safely carry load to harder or more stable layers. So typically, as far as soil strata is concerned, your soft or your weaker soil layers are located near the top, and your stronger, firmer soil layers or weathered rock layers are located near the bottoms. So essentially what a pile foundation does, it allows you to transmit the forces or the weight of your structure past the soft soils and down to the hard soils where it's more resilient or where it's more stable. So that's one of the key strengths of pile foundations, is that you can sort of drill down, or you can transmit those forces down to a more stable strata. Okay, so structures exerting loads like high lateral, tilting, or heavy vertical loads, or structures near the excavation are site risks that that can compromise the stability and that require deep foundations. So, for example, if you have any sort of large-scale loads that include lateral loading or tilting, your pile foundations or deep foundations would be able to resist that much more efficiently and much more safely than a shallow foundation. So load transfer in the pile takes place through skin friction and from pile shaft and end bearing resistance from the pile base. So those two main sort of factors come into account when you're taking a look at your load transfer. It's through the skin friction and then through the pile tip at the bottom. Piles could be designed as skin friction, end bearing, or a combination of both, depending upon soil conditions, the method of installation, and pile material and external loads. So several variables need to be taken into account when they're designed, and these are several of them here: skin friction, end bearing capacity, and then the soil conditions, and of course your method of installation. So these are the main sort of points to take into account from this particular section. So what we'll do now is we'll have a quiz just to go over what we reviewed, just like last week's, or just like the session we had 2 weeks ago. The quiz will consist of 3 questions, and you'll have up to 5 minutes. The quiz itself is fairly simple. 5 minutes is plenty of time. So just take your time and make sure to read each question carefully before you answer it. Okay, perfect. So once again, you'll have 5 minutes starting from now. Good luck, everyone. Okay, I just want to let everyone know that you have 30 seconds left. So for those of you who are still taking the quiz, just try to wrap up real quick, and then we'll move on to the next section. Okay, so that concludes the first quiz. That one I know was a little bit, I guess, a little more complicated or a little more difficult than last week's or the previous session's quizzes. If you have any questions, just email me afterwards, and I'll be happy to sort of go over the quiz with you individually. All right, so now, excuse me, moving on. In this second chapter here, we'll go over pile foundation design methods. So we'll talk about the three main sort of pile foundation types: single piles, group piles, and then pile raft foundations. Okay, so for single piles, we have to start with our bearing capacity assessment. So this equation here is very important. So the ultimate bearing capacity, Q sub U, equals the shaft resistance plus the tip resistance. So Q sub S plus Q sub T. So that's something that we discussed in the previous chapter. Let's discuss a little bit more in detail here. So the ultimate bearing capacity, once again, consists of a combination of these two resistance types. But as you can see, if you have different sort of types of soil layers or sort of soil strata that you're working with, the equation or the values that you use could sort of vary. So for example, if you're using clays or if you're working in clays, you'd have to multiply by a factor of, or for Q sub S, shaft resistance, you'd have to take into account the adhesion. Whereas if you're working with sands, you'd have to take into account the skin friction. So just keep that in mind. When you're working with, depending on the type of soil you're working with, it really affects obviously the total shaft resistance, because the way your soil is interacting with your pile varies. Obviously, stiffer soil types such as clays typically offer anyway, higher resistance. So based on this fundamental theory, numerous theoretical and empirical methods have been developed considering variables in the field as below. So once again, the soil type, cohesive, non-cohesive, soil and rock types all have different sort of skin frictions. Also the installation methods, driven versus cast in place, and then pile material types, concrete and steel. So typically concrete is the material of choice. It does provide a relatively high sort of shaft resistance, whereas steel, as you can imagine, it's much smoother. So the tip resistance, or excuse me, the shaft resistance would be significantly less. Okay, next, then we need to determine the settlements that comprises of these values here. So S sub T, total settlement, equals the elastic settlement plus the shaft settlement plus the tip settlement. So when you're doing your analysis or your design, just make sure that you take into account all of these three settlement types to determine your total settlement. So the tip settlement is obviously the settlement that occurs at the very base of your top pile near the bottom. Shaft settlement is the settlement that occurs sort of on the sides of your pile. The skin friction will resist against the shaft settlement, but there'll still be a certain amount due to shaft settlement. And then also elastic settlement. So whenever you apply any sort of compression load upon your pile, your pile will compress, and there'll be a certain amount of settlement that will result from that as well. So a combination of all of these three settlements equals the total settlement, which is ultimately what you'll be looking for your final design. Okay, now let's talk about lateral behavior of the pile. So whenever you have any sort of lateral load being applied to your pile, there's a certain type of analysis you need to do. So first, let's discuss Brome's method. So this factor beta is applied to determining the lateral behavior of the pile, and it's based on this equation here. Certain variables include the stiffness of the pile section, the coefficient of horizontal subgrade reaction, and also the width and diameter of the pile. So the coefficient of horizontal subgrade reaction, that's typically done through extensive lab testing. So typically you have your soil samples, and you'll have your engineers or your lab workers anyway do significant amounts of testing in the lab. But if you don't have access to that type of research, then there's still publications that are out that give certain ranges of horizontal subgrade reaction values for a particular type of soil that you're using. So depending on the scope of the project, obviously for budgets with very large, or for projects with very large budgets, you'd be able to do on your lab testing. But for projects that are smaller in scale and that don't require that much sort of investment, then you'd be able to just look it up in a publication. So now going on to PY analysis, certain points to be noted. Due to uncertainties in pile-soil interaction, we need to match the results to the PY curve obtained in the field. So therefore, we need to do some integrations. So PY analysis is based on the finite difference method. So as you can see here, I have a pile that's being subjected to a lateral load, and I have 4 different sort of soil strata types. Now it's important to note that each of these PY curves is different from the one above it, or each one is unique. So even though the picture, well anyway, this portion here looks relatively the same, as you can see in the graph here, the PY curve differs. This is due to the different sort of soil characteristics. So just keep in mind that the sort of lateral resistance of your pile is directly related to the type of soil that you're working with. So if you're working on a project with 4 different soil stratas, or in any way if you're working with a project where your pile penetrates 4 different soil stratas, then you need to have 4 different types of PY curves ready to do a proper PY analysis. So another important thing to remember is that these PY curves represent, or they reflect, the nonlinear behavior of the soil. So that's, like I said previously, nonlinear behavior of soil is one of the intricacies, or one of the things that makes soils sort of difficult to work with. So in order to really accurately represent sort of how your pile would respond to lateral loading for each of these soil stratas it's penetrating, a nonlinear sort of curve had to be created for each one. And then, through PY analysis, you can calculate the deflection of each pile segment. Depending on the deflection, you can calculate the soil resistance from the PY curve. And then, as I stated, deflections and soil pressures are interconnected. So as far as PY analysis, I'm sure most of you are pretty familiar with it. There are several sort of programs out there that handle PY analysis. And during the final portion of this presentation, I'll go over SoilWorks and how it handles PY analysis for group piles. And then once again, you have to keep the iterations to obtain the correct values. So PY analysis is an iterative process, but just through numerical modeling programs that are out there, you can actually it does the iterations for you. So the main things that you need to be concerned about are just the inputting the proper parameters for your soil layers as well as your pile. And then, as I said, it is based on the finite difference method. Okay, so let's now compare directly PY analysis versus numerical analysis. So first, soil behavior. So PY analysis, it predicts soil behavior primarily through the PY curve, whereas numerical analysis relies more upon constitutive models, such as the Mohr-Coulomb model. Now, PY elements for the pile elements, they're modeled as beams in PY analysis. So they're modeled as, just these line elements. Whereas with numerical analysis, you have the option of using solid elements as well as beam elements or line elements. The modeling is, for PY analysis, is a beam plus a nonlinear spring. Whereas with numerical modeling or numerical analysis, you can create a 2D or 3D structural model. So for those of you who have experience using both analysis methods, I'm sure you already know that PY analysis is much simpler. It's much sort of easier to use because there's less variables to take into account. That being said, there are more assumptions being made because PY analysis is sort of more conservative. Whereas with numerical analysis, there's many more variables to be taken into account. The modeling takes longer, but the results are much more accurate because more variables are used in the calculations. There are less assumptions being made. Soil structure interaction is based purely, once again, on the PY curve, whereas with numerical analysis, you have interface as well as embedded elements that you use or that the program uses. So what happens is you define these elements and the program uses what you defined to determine the interface, so the way your soil sort of interacts with the pile elements. And we'll discuss this in greater detail later on. And then the upper structure, you can partially model it. Programs such as FBPeer, I believe, has that capability. Whereas with numerical analysis, there's no limitation. You can model both your superstructure as well as your foundation together. Adjacent structures, so you can't take that into account with PY analysis. So if you have like a nearby excavation or a nearby structure, you can't really analyze the effect of your pile foundation upon those neighboring structures and vice versa. Numerical analysis, that is possible. Construction stage analysis isn't available in PY analysis. So if you want to do maybe a sort of a step-by-step construction sequence of a group pile foundation or a pile raft foundation, you wouldn't be able to do that with PY analysis. It's only for the completed structure. Whereas numerical analysis, you can go over each of those steps sequentially. Design applications, it's for conventional, sort of straightforward projects. So if you have a smaller scale project that doesn't require, a very large amount of effort, then you can, very safely use PY analysis. Whereas if you have like a larger scale project, it's, much larger budget and scope and the time it would take to sort of finish, then, state-of-the-art or higher-end modeling programs are used, and they all use numerical analysis just because, with those larger scale projects, there's so much more to take into account. And then as far as the software that's available to you that's in the market nowadays, LPILE, FBP, or SoilWorks, those all handle PY analysis very well. And as far as numerical analysis or finite element modeling, Midas GTS, FLAC, and Plaxis are among the sort of top programs that are used for those types of projects. Okay. So now let's talk about pile groups. So usually piles are used in pile groups and not in a single pile. So typically you'll have a group of piles which are connected near the top by what's called a pile cap, which is this structure over here. So, and the design itself, it'll involve determining how to optimize the best design for the number of piles. So selecting sort of the best organization or configuration of your piles, as well as how many piles are being used. So the spacing, the layout within the foundations. Typically, you'll have several different sort of layouts that you want to try, and you'll run the analysis for each and see which one works best for your project needs. And as far as the pile cap, it mainly serves to distribute the load coming from the top properly to the different piles and to connect these piles to the superstructure. So that's pretty straightforward. As far as the way your forces will be distributed, they'll be pressed upon the pile cap. The pile cap will distribute them to the soil, and then the soil will transfer the loads to the the pile cap will transfer the loads to the piles, and the piles will transfer the loads to the soil. And then, I'm sure you've all seen sort of this overhead view before. Your center to center spacing of your pile is outlined as such. So some important sort of concepts to remember when you're designing pile groups. So the ultimate capacity of piles may not be equal to the number of piles multiplied by the capacity of a single pile. So you can't just do the analysis for one pile and then multiply it by how many other piles you put in the group and get your total capacity. It doesn't really work that simply. And also the ratio of the pile group capacity to the total load capacity of the piles acting as single piles is called the group efficiency factor. So another important thing to keep in mind when you're designing a group pile. So the group efficiency factor is dependent on the number of pile rows and the number of piles per row, spacing, and the diameter of the piles in the group. So once again, the group efficiency factor, or how well you're sort of making use of your configuration, depends on just the way that your piles are spaced, as well as the size of the piles themselves. Okay, so now let's discuss pile raft foundations, which, as I stated previously, are for sort of larger scale structures or larger scale projects. So pile raft foundations provide for an economical foundation option for circumstances where the performance of the raft alone does not satisfy the design requirements. So under these situations, the addition of a limited number of piles may improve the ultimate load capacity, the settlement and the differential settlement performance, and the required thickness of the raft. So pile rafts have appeared to be an efficient way, or an economical way anyway, to provide foundations for these types of high-end structures. So in the beginning, it was taught to only use a limited number of piles at settlement under the rafts, and later on to have these very high-rise buildings become integrated in the system between piles and pile rafts instead of using a limited number of piles. You can also end up using hundreds of piles under a raft of maybe 3 to 5 meters of thickness. So once again, for very large-scale projects, you can end up using a very large amount of piles, which takes a very long time to analyze, which is very complex behavior. So naturally, you can only really realistically model these types of projects with a high-end sort of program, or with numerical modeling. PY analysis, you wouldn't be able to do it efficiently or accurately. So certain advantages of pile raft foundations include the following. You can sort of limit the number of absolute and differential settlements. So for example, if you have a large sort of scale sort of structure, and say it has lateral loading coming from the wind, or if there's maybe a tower on the superstructure that's higher, naturally you're going to have a greater you're going to have a difference in sort of the weight or the force distribution, which could cause over time the superstructure to maybe settle awkwardly. Maybe, eventually one part of the foundation will be higher than the other. But with pile raft foundations, you can actually sort of simulate the how these forces are unbalanced and change the design to counteract that. So, ultimately when you have, the superstructure is completed, even though there's sort of an odd or asymmetric distribution of forces, your superstructure will stay level because you've designed your pile raft foundation to take those into account. And we have a case study that sort of goes over this concept in greater detail, and we'll share that with you during the second to last section of this session. And once again, the advantages of pile raft foundations. So as I said, it limits the absolute settlements and differential settlements, reduces foundation and tilting, either due to load eccentricity or irregularities in the subsoil, and then a reduction in raft internal stresses. So just sort of a recap of the points I brought out previously. All right, so let's talk more about pile raft foundations, and in particular, the design philosophy behind them. So the main objective of pile group design is to ensure that the foundation does not undergo excessive displacements, so also known as a serviceability limit state. So there's a certain limit that you don't want to pass as far as your displacement. So additionally, often a factor of safety against collapse of a pile is required. So this is also called the ultimate limit state. And then the real ultimate limit state must be determined by considering the interaction of foundation and the superstructure. For those of you who've worked or who will work anyway with pile raft foundations, you'll need to work very closely with the structural engineers. I understand that usually it's sort of a back and forth. The geotechnical engineers will provide certain design considerations to the structural team to use. They'll run the analysis on their end, and they'll have certain specifications that they maybe need to meet later on that they'll send back to you. So once again, it's an iterative process that goes sort of back and forth between structural and geotech engineers in order to ensure that all the design goals are met. Also, the ULS, or the ultimate limit state, then reverts to a displacement criterion that is determined by structural considerations. So once again, it's very much a team effort between the geotech and the structural engineers when pile raft foundations are designed. Okay, and then also the bearing behavior of a pile raft. The behavior of pile raft foundation is much more complex than single or even group pile foundations. So you can do away with the PY curve approach, several iterations for a single pile or for a group of piled rafts. But I think use of numerical analysis programs like, for example, MIDAS-GTS or Plaxis for 3D analysis is absolutely necessary. So here's the reason why. So pile raft and their bearing behavior is a very good example for soil structure interaction. If we have a look here at this diagram on the left, we have a raft separated from the piles so that the raft itself has its own interactions with the soil around it, and the pile has interactions with the soil around it. So you have two different types of interactions, pile to soil and then soil to raft. And the interaction between the pile and the raft, or the piles and the rafts themselves. So the third interaction you have to take into account is the interaction between these piles and the raft. So now we're up to three different types of interactions. So these interactions, they're very, very critical in governing how the piled raft will behave or perform and its ultimate bearing capacity at the end. So ultimately, the total bearing capacity of the piled raft will be the summation of the bearing capacity of the piles plus the bearing capacity of the pile on the raft. And the pile bearing capacity is in itself a summation of the base capacity plus the shaft capacity. The raft's bearing capacity is at the contact stress over the area of the rafts. So if you look to the right here, as you can see, we have just listed here all our different sort of interactions. And all of these need to be taken into account when designing your pile raft foundation. So even though maybe from sort of on the outside it looks very sort of simple as far as how the design or how the structure works, there are all these variables that need to be taken into account in order to really design an optimized pile raft foundation. So, as you can imagine, in order to do something like this by hand or by spreadsheet would take, a very long period of time. It would be sort of a very painstaking process. So once again, that's just another advantage of numerical modeling programs in general. So you have large-scale projects with these types of variables. Your main focus ultimately will be to design or to create a model that simulates all of the input parameters that you have. So for example, you just need to make sure your soil properties are correct, the dimensions of your power raft are correct, that you have a configuration that sort of works as a starting point. From that point, you can run the analysis. You can see how close it gets to your ultimate bearing capacity or your limits that you set, and then you can go back and make the make the adjustments to the design. So it's this iterative process once again with the structural engineers. But just keep in mind that when you run the analysis on any sort of numerical modeling program, these interactions are all being taken into account. That's why I know for a lot of large-scale projects such as the power rafts, the analysis can take quite a long time, maybe up to an hour on even the most high-end programs. So that's why the analysis itself takes so long. It's just because there's all these interactions that need to be taken into account and to be analyzed and computed for. Okay, so now let's talk about single piles versus pile rafts. So this is just this graph to the right here is anyway just sort of a direct comparison of how each sort of pile type behaves. So as you can see, the piled raft, it's much more resilient. It has much more resistance and much less settlement as the force sort of increases, or as the resistance increases. Excuse me. So as you can see, if we go look to the single pile here, the single pile, it'll have a certain amount of resistance, but then it reaches a relatively early breaking point or a failure point. Whereas the pile group, it's a little bit more resistant, and the breaking point is further out. But with the power raft foundation, it's sort of optimal, or sort of the most resilient anyway. So as you can see, the breaking point isn't really sort of reached. It just sort of gradually reaches failure. So just keep in mind that as far as settlement, your pile raft foundation is your most resilient and your strongest. And then let's talk about single pile versus pile raft. So once again, this is just this diagram anyway, just sort of illustrates how each of your piles in your group or your raft foundation behaves. So depending on where the pile is located, it also has a sort of a different way to react towards the resistance. So as you can see, these inner piles here are the most supported. This has to do mostly because when the load is distributed, this pile shares the load with the pile to its to the left, to the right, to all around it. Whereas piles on the edge or on the corner, the force it has less distribution, so it's taking more weight. So as you can see, a single pile working by itself would have that sort of same sort of behavior that we saw on the last slide. Whereas corner, edge, and inner piles all behave or all react very differently because of the way the force is distributed. So as you can see, the inner pile is the most resilient just because the force is distributed to the other piles around it. Whereas edge and corner piles are more quick to sort of go to failure based on the amount of resistance pressed upon it. So that might be something that we'd want to take into account. Just how your force is distributed to your edge and your corner piles, because these corner edge piles are very critical in your design. Okay, so now let's talk about certain design requirements for the pile raft foundations. So SLS, serviceability to limit state, is a decisive criterion for the design of vertically loaded pile rafts. Also, the magnitude of absolute and differential silt settlements and tilting of buildings are therefore of special importance. For example, especially high-rise buildings. So some questions arising in the design of pile rafts that you need to ask yourself are one, what is the sort of relative proportion of load carried by rafts and piles? And then also, which pile configuration, the number of piles, pile lengths, and layout reduces the absolute and differential settlements and structural forces most efficiently? So these are two sort of very determining or very key factors that will come into play when you're designing your pile raft foundation, especially this one, so which pile configuration. So naturally you'll have maybe several pile configurations to choose from and to keep in mind. Usually you'll have sort of an iterative process where you'll design one pile configuration that's sort of over-designed, and you'll reduce it until you find a design that's not only sort of stable and efficient, but also economical. And then numerical modeling requirements. So for those of you who are or will be working with Pile Raft foundations, numerical modeling requirements are, things that you'll need to take into account whenever you're creating your model. So when you're creating your model, you should keep in mind that the model should be able to consider the three-dimensional behavior of the Pile Raft foundation. So this is key. You can't really model Pile Raft foundations in 2D. As I said, or as we stated previously, the inner and corner piles behave very differently. So in order to really capture accurately the behavior of a Pile Raft foundation, it has to be done in full 3D. Also, you need to simulate the behavior of a single pile to check its reliability and adjust the applied parameters depending on the chosen pile type. So that's another sort of iterative process, is sort of determining the parameters of your single pile. Also, the applied constitutive laws should be able to take these things into account. So the nonlinear / pile soil behavior at the pile shaft and pile base, as well as a stress-strain behavior of the soil depending upon the applied stress path and strain level. So once again, this just goes back to your input parameters. You just have to make sure that all of the data that you put into the program is reliable and accurate. Naturally you'll have lab tests and field tests at your disposal to make sure that these constitutive laws are met. And also the applied model should be able to consider the different interactions that govern the behavior of the piled raft. So that just goes down to modeling interface elements, making sure that all of your parameters represent accurately just the behavior of your soil against your piles, as well as the piles against the raft. And once again, we'll talk about that in greater detail in the next section. But these are just certain interactions. These are certain variables that are very important when you're doing your numerical model. Okay, and then just the design process of Pile Raft foundation. So as we discussed previously, it's a very iterative process. So first you have your geotechnical tests, lab tests, field tests to determine the strengths and characteristics of your soil. You'll also have pile tests to determine the strength characteristics of your piles. And then from that point, you'll create a numerical model on a software program or geotechnical program. Once you create your model, you'll run the simulation, so you'll get your results. Typically, a parametric study, that's just another way of saying multiple case study. So you'll have several different cases that you'll model. You'll compare them against each other. You'll have different load combinations that you'll want to model. Then it'll go back to the model simulation. So it's sort of this iterative process where maybe you make some adjustments to your model based on the results. If the results that you have aren't optimal, you'll want to go back and change your model and then see what your results are again. Then once you create your model, there might be some calibration that needs to be done. Once again, that goes back to your model simulation. So rerunning the analysis after making changes to your model. And then once you're ready, you can submit a foundation design to your structural engineers to review. So as far as your foundation design, the serviceability limit state and the ultimate limit state, these are two criteria that really need to be brought to the forefront, or that need to be, or anyway, that the structural engineers will be looking out for when they do their structural design. So the structural engineers, using what you give them, they'll make certain design choices with their design, but they may need to go back. They might need to go back to you and ask you to maybe make some adjustments to your model in order to better fit what they have in mind. So that's another sort of the second sort of iterative process that you're working with here, is going back and forth between the structural engineer. Okay, so just in summary, I know it's a very long section, so let's just review what we went over before we have the quiz. So single pile behavior needs the estimation of bearing capacity, settlement, and lateral behavior. For lateral behavior, PY analysis and numerical analysis are very commonly done. Numerical analysis has the advantage over PY analysis as it saves iterations and approximation. Pile Raft foundation limits absolute and relative settlement, prevents tilting, and reduces raft stresses. So those are key advantages of Pile Raft foundations. Pile Raft system reduces the pile stiffness and increases the bearing capacity, and thus prevents failure. Governing criteria for the design of a pile raft is settlement, or the serviceability limit state. Pile raft foundation behavior involves pile-to-pile, soil-to-pile, raft-to-soil, and raft-to-pile interaction, making conventional analysis obsolete. So once again, there's really no way that you can approach pile raft foundation design or analysis with conventional methods. It has to be done through a finite element model, through a program. And then 3D numerical analysis, as I said, must be done for Power Raft Foundation. So these are the main sort of key points to take from this section. Once again, I know we went over a lot of material. I went through it pretty quickly in the interest of time. So don't worry, I'll send you all a copy of this PowerPoint at the conclusion of the session. Oh, and then also the numerical model must be calibrated with the field data, and constitutive laws must reflect the interaction. So that's pretty straightforward. You have to get your field test first before you create your numerical model. All right, so now let's roll into quiz 2. Once again, it will be 5 minutes, 3 questions, multiple choice. I'll bring it up now. And I'll make sure to give everyone a 1-minute warning once we reach the 4-minute mark. Okay, everyone, we have about 1 minute left. So for those of you who still haven't finished, just try to finish up your last couple of questions, and then we'll move on. Okay, thanks for your participation, everyone. So now we'll move on into the third section. So numerical analysis for foundation design. So we'll go over different Powell modeling methods, how to verify results, and then things that need to be considered in numerical analysis. So when it comes to numerical analysis or finite element modeling, there are three main approaches available to you. There's a solid element model, also known as a solid-to-solid interface, the beam-to-solid connectivity model, as well as a line-to-solid interface model, also known as the embedded pile. And we'll go over each of these modeling types in detail. So first, let's talk about the solid element, or the solid-to-solid interface. So essentially what you're doing when you're creating a solid-to-solid interface is you have a model, or a complete model, that consists of all solid elements. So as you can see, this pile here consists of solid elements. So what the engineer has done he's taken his pile, and as you can see, it's just a single pile. So he's taken this pile and he's divided, or he's meshed it into, a sort of a set of finite elements here. And he's done the same with the soil, which, when you're working with finite element analysis, you'll always do the meshing for your soil. But however, as far as, meshing your pile, that's sort of optional. So there's certain benefits and advantages, or, benefits and weaknesses anyway, when you choose to mesh your pile element as well. But also keep in mind that in addition to just your pile element being meshed, there is also a series of interface elements that have been created along the surface to model your pile to soil behavior. So that's once again, this is the first model, solid to solid interface. And the main thing to remember is that what makes it sort of unique as far as the modeling is that the pile element has been fully meshed. So let's take a look at how this sort of affects our analysis. So main points of attention for solid element models. So the model definition and mesh generation can be elaborative for a large number of piles. So this is just another way of saying if you have a very sort of large-scale model with maybe a dozen piles, or up to 100 piles, then creating a mesh set for each individual pile might be a bit cumbersome. It might be a bit too much. Just keep in mind that the more that you mesh, or the larger amount of elements that you have in your model, the longer it takes to analyze. So even though if you choose, or if you elect to do to mesh your piles, you'll get very highly accurate results, but also the analysis could take a very long time, especially when you have a very large set of piles. So as I just discussed, many elements in the model contribute to a very long computation time. Also, pile forces and moments are not directly available in the post-processing. So even though finite element analysis, or creating 3D elements for your pile, are very good for the displacements here, as you can see, all the nodes are just sort of connected. Here's your sort of your interface element, and all of your nodes are just interconnected, where you can get very good displacements. You can't get for example shear force or axial moments, or axial forces, or moment diagrams for your pile. So if that's something that you need, just keep in mind that solid elements can't represent that, or can't be used to calculate that. So that's one shortcoming of solid elements, actually, is that you can't get your moment diagrams for your piles. You can't get your axial shear diagrams for your piles either. And then also, interface behavior, also known as elastic, nonlinear elastic, and Coulomb friction, are user-defined behaviors. When you're creating your interface elements, you have to make sure to get all of these parameters and input them into your model. So interface behavior and sort of the the material properties of your pile and your soils. Those are sort of three different categories. So in other words, when you create your model, you'll input your parameters for your soil, for your pile, but then you also have a third category which is specifically for interface behavior. So it's important to not forget to define that behavior when you're creating your model. Okay, so our next analysis type or modeling type is called the beam solid connectivity model. So as you can see, the soil is meshed once again, but this time the pile is represented by a beam element. So when you when you do this, what you're doing is you're telling the program that this beam element has certain sort of characteristics or material characteristics, for example, a diameter, a length, etc. But when the analysis is run, the program will model the pile as a beam element, just for the sake of simplicity. So as you can see, because the pile itself, it's symmetric, and the properties are uniform throughout as far as geometry, it's very convenient to model this as a beam element. So main things to remember. There's no interface elements for a beam to solid connectivity model. It's just a beam to solid connection. So what happens here is your links, or excuse me, not your links, your nodes, they're linked directly to your solid elements. So as you can see, one of these represents just for example, a solid element, or the neighboring solid element to your pile, and these nodes will overlap. So anyway, the nodes will be shared between the solid elements and your beam element. So that way, the displacement, will be uniform. So for example, if the soil shifts, x, a number of inches, the same principle applies to the beam element. The beam element will also shift x number of inches depending on its placement. So main points of attention for beam to solid element models. The nodal compatibility requirement makes geometry modeling and meshing of the soil elaborative. So because your solid element needs to be directly connected to your beam element, it can make the modeling itself, the analysis runs very quick because it's a beam element, but the modeling can take much longer because it takes time to really make sure that all of your nodes are connected. That's something if you have like a very large scale model with all these beam elements, the first go around, it'll take a little while, but you can do it so that all of your nodes are connected. But let's say, for example, you need to go back and you need to make some changes. Well, that can take a very, very long time. This is something I've had, unfortunately negative experiences with, is going to have to go back and to change my model and to redo all the meshing, reconnect all the nodes. It's something that can take a very long time to do. So that's one of the main sort of deficiencies, or not really deficiencies, but I guess weaknesses of using this type of method, is that for larger scale projects where you have a lot of reiterations or redesigns, or you want to change your geometry, then having to make those changes can take a very long time. Just because of the way your model is set up, because of the way the nodes need to be directly connected to your solid elements. So, just keep that in mind before you begin your model, or when you're choosing your model anyway. Just make sure to keep in mind this shortcoming of the beam solid model, is that it makes reiterations, or redesigns very difficult. One of the strengths, though, is it has a very sort of short computation time for smaller scale models anyway. But for pile rafts with a large number of piles, this technique produces large models with a very long computation time, just because of the large number of nodes. So this is typically used for, I guess, these smaller group piles. For example, bridge abutments. I've seen this method used a lot for bridge abutments. Whereas if you have like a large, high-rise buildings or large structures with large pile raft foundations, then this method is hardly ever used. In fact, I've actually never seen it used for a pile raft foundation, just because of the complexities of linking up all your nodes. Okay, so the third method, or the third model that we'll talk about, is the line to solid interface model. So the main thing to remember about the line to solid interface model is it uses sort of a combination of the solid to element of the previous two models anyway, to achieve something, I guess, a little bit more convenient, or actually much more convenient for pile raft foundations in particular. So the pile is modeled actually with a special element called an embedded pile, as represented by these red boxes here. It's called an embedded pile element, and it has the property of a beam to allow for the extraction of moment and bending forces, which is very key. So even though in the previous method, in the beam to solid model, you could get your sort of axial forces as well as your moment diagrams. Doing the interface is very difficult because of the ways you have to line up your nodes. But with the line to solid interface model, I'll discuss it in the next slide actually. You actually don't have to line up your nodes. It's all done automatically for you. And also, because you're modeling part of the pile anyway as a beam element, you'll be able to get your moment diagrams. So this interface element, once again, it allows for soil structure interaction, but the way that the pile is modeled as a beam element still allows for moment diagrams and shear diagrams. So it's really a combination of this beam element plus these interface elements here. So which makes it a very sort of versatile sort of a method to use, especially with pile raft foundations. That as far as doing your redesigns. Actually, let me go to the next slide here to give you a better idea. So here we have the line to solid interface model. So here are a couple of characteristics. So as you can see, this square, or these sort of tetrahedral elements here, represent your solid elements of your soil, and these line elements here, these beam elements, represent your pile. So as you can see, you can just sort of directly embed the pile within these solid elements. And pile and soil geometry, they can be specified independently. So that's just another way of saying that you don't have to worry about directly interconnecting your pile and your soil geometry. You can model them sort of independently. And then the intersections of line and solid elements are calculated automatically, which is very, very key. So you actually don't have to model the intersections yourself. Just because of the way that this method or this model is sort of set up, the program can actually directly or just automatically calculate those intersections. Which is very important. So if you happen to go back and redesign, maybe or make some changes to your model, you actually don't have to redo all the meshing. You don't have to line up all the nodes. The nodes will just line up sort of automatically for you. Or actually, technically they don't really line up, but the intersections, they're computed automatically for you, so that you don't have to worry about those intersections. It's all done for you. Also, nonlinear friction slip properties for line solid interface elements. So once again, when you're creating this or when you're doing this model, you have to come prepared with your interface material parameters. And the properties are for a line to solid interface, which I'll show you a detail of that later on. And then also mesh refinement requirements for the soil are minimum. So you don't even have to have the soil itself to have a very highly refined mesh or very small mesh. You can actually get very accurate results with a very sort of with a sort of larger scale, or not larger scale, but larger mesh sizes. It also includes a reduced computation time. So the main strength of the line to solid interface model, once again, just to reiterate, is that the connections or the intersections of line and solid elements are done automatically. So you don't have to worry about creating them yourself. Which once you start doing this, you'll see how it saves you so much time, especially when you're fine-tuning your model. And the reduced computation time obviously leads to faster analysis times as well. Okay, so here we have just a sample. So what we're going into now anyway is just how to sort of compare the computational or modeling results to actual field tests. So naturally, whenever you do any type of analysis, it's always good to have a field test to compare it against, just to make sure, or just to check the results of your work. So this setup here was used to calibrate the bridge foundation, and it's still a valid example for numerical models today. And it's actually for a bridge foundation in Germany. So here, under this setup here to the left, the pile is embedded, and here we have a couple of sensors here just to analyze the friction, as well as these load cells here to analyze or anyway not to really analyze, but to record the bearing capacity. And here's the measured behavior. So here we have our base load, our skin friction, and then our total load, or our combined load. And then what we do is we'd have the results of that test just for a single pile, and we compare it to the results of our numerical model. So ultimately, you'd want obviously these lines to be as close as possible. So M total, M skin, and M base, those correspond to the test, and then total skin and base. These three lines here, the straighter lines, represent the model. So ultimately you'd want your you want the results of your model to follow roughly the same trend as the ones given by your field test. If there's a very large or distinct separation between the two, then obviously you need to go back and check your work. Once again, here's another sort of example. From a simple model to a complex model, the types of results that you need. So here you have your FEM analysis and your PY analysis. These should be, very close. This is deflection versus lateral load. Same with you say you have like multiple piles, you'll have all of your graphs sort of superimposed against each other. So you just want these to be as close as possible. Once again, if there's a vast or a significant differential between your results, you need to go back and check your work, because there's probably some sort of error, some kind of variable that needs to be changed or that's been sort of left out. All right, so the main things to consider in numerical analysis. These are the questions that everyone needs to sort of ask themselves. So what is the most important behavior in a model? Behavior of single piles, group piles, axial or lateral, adjacent structures or superstructures, soil-structure interaction. So depending on what's most important really sort of determines which sort of numerical modeling method you'd use. If you have a single or a group pile, you could use solid-to-solid element or solid-to-line element. Whereas if you have like a sort of a larger scale pile raft foundation, you'd use the last method that I showed you with the soil structure interaction elements. And then accuracy versus efficiency. So for more complex geometry, obviously it requires more time. There's a greater investment, especially when you're dealing with asymmetrical geometry. It takes time to model that in 3D. And then efficient modeling will reduce the analysis time, so proper elements, symmetric array, sabermetric models. So it's really important that the bulk of or a large portion of your time be spent on making sure that you have an efficient model. If you don't have an efficient model, then the sort of time it takes for you to run the analysis and ultimately finish the project will be compounded by a very large degree. So typically the way to avoid that is just to make sure to invest a sort of a good deal of time creating a very efficient model, checking everything. Because if you try to speed through your model the first time around, ultimately it could lead to a lot of problems in the future, which ultimately would lead to you taking more time to go back and change the model, etc. Okay, so just a summary of this chapter. 3 modeling approaches exist. Solid to solid is typically used for single pile or small group piles. Beam to solid, which is used for typically bridge abutments, small group piles. And then the line to solid, the embedded pile, which is typically used for pile raft foundations. The embedded pile approach has a beam element to represent the pile member and a friction tip bearing interface element to represent the pile to soil interaction. So that's very important to remember. Is that the beam element, is used to get your, your bending diagrams, your moment diagrams, and the bearing interface elements are used to represent your soil structure interaction. So it's very unique in that aspect. And then advantages of using the embedded pile element are pile and soil geometries and mesh can be generated independently, so it's very easy to go back and make changes. It's very easy to create your beginning model or your initial model. The intersection of line and solid elements are calculated automatically, so that's, with the beam to solid element, you have to do that, by yourself manually, which is okay for smaller scale projects, but if you have like a really large scale project, then it's very time consuming. So that's one of the key advantages of the embedded pile or the line solid model. And then nonlinear friction slip properties can be accounted for through interface elements very easily. So yeah, as long as you have interface properties that you can really rely upon, that you're sure about, you can just input them into the program and that'll be taken care of for you. And thus the models are lighter, efficient, and take less time to run. So that's just another key advantage of the line to solid model. And then the numerical model must be verified with field test data of a single pile prior to generation of a complete group or pile graph model. So just going back to your field test, you'll always have to go back and compare them to your numerical modeling results just to make sure that you're on the right track. And then the selection of modeling approaches depends upon, once again, the objectives of your analysis. So once again, solid to solid is, it sort of goes from smaller to larger scale. So for very small sort of scale projects, you can use a solid to solid model, without any trouble. Intermediate projects, the beam to solid this beam to solid model is best used. And then for larger scale projects, the line to solid or the embedded pile model is most efficiently used. Okay, so now on to the final quiz. It'll be 5 minutes once again, 3 questions, all multiple choice. And I'll give you once again a warning once we reach the 4-minute mark. Okay, everyone, just want to let you know that we reached the 4-minute mark. So for those of you who are still wrapping up, just make sure that you get done within the next minute. Okay, thank you, everyone. So now we'll move on to to Chapter 4. So now we have a case study of a tower that was constructed in Dubai in the United Arab Emirates. So this case study was actually submitted by Kostas Singros and Alan Popel of Langen International. This was a project that they worked on extensively, so we're very thankful to them for volunteering to submit this case study. It involves the soil foundation superstructure interaction for tall buildings on pile foundations. So let's dive into sort of the parameters here. So the superstructure, the tower itself, consisted of two adjacent towers connected with a bridge. So the tower was built in Dubai, very close to the Burj Khalifa Tower, which is the tallest building in the world. Also, that was worked, or the foundation actually was designed by Langen as well, from this office, or from the Langen office in New York City. And then the tower heights were actually unequal. So the towers were approximately like 60 stories each, but one was a few stories taller than the other. So as you can see, the asymmetrical loading had to be taken into account, which is why the polygraph foundation design was so sort of critical in this type of project. So the polygraph foundation consisted of about 164 piles per tower, and the pile raft itself was about 3 meters thick. So it's a very large-scale project, a very large-scale foundation. But as I discussed, it was a pile raft foundation system. And then the building code required the total load to be taken by the piles. So zero could be contributed by the subgrade. So that was sort of a unique design consideration that need to be taken into account. So let's discuss now the geotechnical investigation that was involved. So first, geotechnical borings. They had to be done obviously in situ testing, SPT, pressure meter tests, etc. Laboratory tests were extensive, so index properties, triaxial testing, 1D consolidation. So all of the materials were tested extensively, in the lab and on site prior to the design, which is to be expected for a project of this scope. Pile load tests were done to check the, the structural sort of properties of the piles they were using. And then literature review. So they made sure to review all of the sort of preliminary design or preliminary sort of literature criteria that was given to them to make sure that everything that they were designing, or the pile foundation that they were designing, met all the criteria that was necessary for this particular site in the project. So just to make sure they met all the client's needs anyway. And then model parameter selection. So they needed to determine critical parameters such as the raft thickness, the pile raft thickness, location, as well as the geometry of the pile. So this is something that could take a very long time to do, is to determine the pile configuration. So in order to determine the configuration that would be best suitable towards the project needs in terms of being economical, as well as being sort of safe for the project and designing a very firm foundation. Soil modulus of deformation is another key factor. So the soil needed to be tested to make sure, so that they could design with confidence that the soil has this sort of strength or these sort of characteristics. That way the piles can be designed accordingly to take advantage of the soil's weakness, or to take advantage, of the soil's firmness, or to overcome the soil's weakness, depending once again on the strata that they're working with. And then the method of construction. So the way the piles were constructed, sort of step by step, how that would be taken into account for the design as well. And then the pile to soil interface strength. So another key factor is determining the characteristics of your soil structure interaction elements. So now let's discuss the parameters that need to be taken into account for their finite element modeling. So the input, the geometry of the raft, the piles, and the stratigraphy. So naturally they needed to make sure they had all of their geometry ready for them, as well as their sort of location geometry available to them and ready for them before they started doing their finite element modeling. Material properties for the raft, piles, and stratigraphy. So there was a great deal of sort of data collecting and investigation before the actual modeling and design work began. Element selection as far as volume, area, line elements. So we'll go over the type of modeling they did in the next couple of slides. Boundary conditions, obviously those are very important. Loading, so there are many different sort of dozens of load combinations that need to be taken into account. So construction staging loading, overburden, self-weight, as well as the tower loads. And as we specified, one tower was taller than the other, so there was an asymmetrical load that needed to be accounted for as well. Okay, so here's just sort of a couple of screenshots of what their finite element model looked like. So this is an example of their soil strata. So as you can see, here are the two main sort of pile raft foundations that were designed. They were embedded into the soil strata just through, so the pile raft elements anyway, as you can see, these are 3D sort of solid elements. But if you go to this sort of cross-section view here, you'll see that the pile elements are actually beam elements. and they actually have the interface modeled on them. So these are embedded pile elements that were used. So this is sort of a far away screenshot, but we'll get some closer screenshots or result screenshots in a couple of slides here. So let's talk about the typical rock and soil constitutive models that were used. So for soil, the elastic properties were determined, so the modulus elasticity, Poisson's ratio, and unit weight. And then for the more Coulomb material property, the friction angle as well as the cohesion was determined. So one thing I want to point out is the more Coulomb model is used typically for limit state analysis. In other words, for bearing capacity, self-stability analysis, as well as wall stability. So within your finite element modeling, you have these different constitutive models available to you, each of which is used for its own specific purposes. And then the modified more Coulomb, also known as a soil hardening model, is used for pile, retaining wall deflections, as well as supportive deep excavations and consolidation. So actually something that one of the attendees of last week's session brought up to me was the difference between the more Coulomb and the more modified more Coulomb model, also known as a soil hardening model. So I was very thankful for that. So for those of you who want to maybe sort of share maybe publications with me, or who maybe feel that more could be added to my presentations, definitely don't hesitate to contact me. Thanks to the person who emailed me the information about the different models last week. It was very helpful to me. And then also the soft soil, or the modified Camp clay model, which is used for consolidation analysis for settlement over a long period of time. Or if you're working with clay soils, this is what this constitutive model is used for. So as you can see, because it's a very large-scale project, all of these constitutive models were used, and each of them served their own specific purpose. Now for rock, the elastic constitutive model was used as well, and then the more Coulomb, and then the Hoek-Brown constitutive model, which is specifically for rock analysis. So this is something to be discussed in maybe a later presentation. But the Hoek-Brown, whenever you're working extensively in rock, you'll be using this constitutive model in tandem with the more Coulomb model, which is used for soil. Okay, so here we have the, as you can see, sort of a rehash or recap of what we went over last time. So when deciding on what type of model they wanted to use to model their pile raft foundation, they had these three options, and they came to these conclusions. So as far as a solid element model, this is the best, but model may become too big for the computer to handle. So as we discussed previously, the pile raft foundation for this project consisted of over 100 piles. So for a computer to handle a solid element model was very sort of unrealistic. Even though the solid element material model provides highly accurate results, just the level or the amount of computing that would need to be done would just make the project sort of too cumbersome to do with this particular model anyway. Then the beam solid connectivity model is sort of an intermediate situation. So as we discussed previously, nodal connectivity is required along the entire pile length. So even though it would be more efficient than the solid element model, ultimately because nodal connectivity is required along the entire length, design changes or adjustments to pile configuration, etc., will take a very long time to do. So even though it's a better option than the solid element model, ultimately the best option was a line to solid interface model, because they can sufficiently and accurately handle a large number of piles. Once again, because it's sort of a hybrid combination or a hybrid modeling method. So it uses beam elements or line elements to model the piles, but it also combines them with these interface elements or these embedded elements to account for soil structure interaction. And once again, because no nodal connectivity is required along a pile length, in other words, that's all sort of the way that the intersections are done is automatically done by the program. It's very easy to make revisions. So ultimately, this was the type of model that they chose for their pile raft foundation design, was the line to solid interface model. And then now let's talk about the loading conditions. So for example, they had to account for the soil, the foundation, self-weight, column and wall loads such as point loads, line loads, and pressure loads. So as you can see, this is the finite element model, and each of these green arrows here represents sort of a point load. So as you can see, they sort of individually modeled just a distribution of loading along their pile rafts. And it's all done in 3D here. And also the foundation construction stages. So obviously when the foundation was constructed, it was constructed piece by piece. And because it was constructed, piece by piece, section by section, the loads changed as well. So that was something they took into account. They modeled a stage for each sort of combination of loads. just to ensure that safety would they could ensure that the site would be safe during construction. Okay, so now let's talk about the settlement results. So these are just the results of their final element model. So once again, this was modeled with minus GTS, and the displacement, as you can see, is sort of maximized in the center here by these red contours. So as you can see, each of these represents the different sort of section of the pile foundation. And as you can see, the displacement is relatively sort of uniform. There aren't exactly mirror images, but they're very well within range. So obviously this is the final design, so this is what they wanted. They wanted to make sure that the ultimate settlement or the long-term settlement would be sort of equal for both sections of the building. So this, I'm not sure which one had like the taller tower, but also there's other loads to account for, wind load differences and lateral loading. The bottom line is they wanted the settlement to be relatively equal for both of the towers, which is what they were able to accomplish for their final design. So the simulation sort of showed that long-term settlement would be equal for both of the towers. That way they could ensure that the years from now the structure would still be level, even after extended periods of settlement. And also settlement results, just sort of a side view here. As you can see, they could very sort of determine or simulate where the maximum settlement would occur. Naturally, it would occur towards the center of the pile raft foundation. And this is just for one of the pile raft foundations. They did it for both, and they made sure that within reason they were close enough. And then also vertical strains, also known as block behavior. So in order to analyze, obviously the effects or the sort of the strain acting on the tips of all the piles, as well as soil strains, they were able to determine using that option on the result menu. And also pile settlement, which is very key. So as we discussed previously, the piles in the center, they have the most load distributed among them. So although they have they don't sort of fail at an earlier rate. They do have a greater degree of settlement as shown here. So as you can see, maximum settlement occurs near the center. So once again, with each of these pile raft foundations, they just wanted to make sure that the settlement was relatively sort of equal or close to enough within that range. So that they could say with confidence that the settlement will be equal, that ultimately the towers or the overall structure would remain level after long-term settlement. So that was another way that they would be able to sort of check their settlement to make sure that the loading or the settlement anyway was equal. So even though the loading is unequal, the settlement is relatively equal, which is very key for this design. And then also the pile axial loads. So it's a little hard to see here, but as you can see, because they are beam elements, here you have all of your axial load diagrams. So for over 100 piles, they were able to get the individual axial load diagrams for each of them, and they were able to check them individually. So they modeled them all at once. They did the analysis all at once, but they were able to check the results individually, which is very key. So for conventional approaches, obviously you'd have to model, analyze them, each of them individually, which would take extremely long time to do. But because they had finite element modeling at their disposal, Costas was able to take care of all of the modeling and to check all of the loading. So once again, if you have someone in your firm or you have someone in your company who's very adept at finite element modeling, someone such as Costas or Alan, you'll be able to really speed up the really be able to do your analysis much more efficiently. Okay, then pile to soil relative slip displacement. So, I'm just sort of going through the different results that are available to you. But once again, when you have a large-scale project such as this, you'll want a wide range of results. Obviously the client is going to want to make sure that everything's been accounted for. So, when you have a program such as MinusGTS, you can get all of these results. You can display them all very, very clearly. So once again, your relative slip displacement, at a glance, you can see, it's relatively sort of similar for each of the pile foundations here. And then the pile loads plus the settlement. So here are the pile loads. So as you can see, each of these piles receives a different sort of loading, just depending on where it's located, which tower it's under, etc. So another thing that they needed to do was they need to sort of model individually which piles receive what kinds of loading here, as well as the pile head settlements. So as you can see, it's a very highly detailed model. All the loads are very, they were sort of individually inputted for each of these piles. Settlements were individually calculated. Well, I guess technically they weren't individually calculated. The analysis was done at once, but you get individual results for each of your pile head settlements. So as you can see, because you have this sort of level of analysis, you can get results that are very detailed and that you can sort of have with confidence to make sure that your pile raft foundation is up to par with the client's needs. And then also the soil springs. So they had to provide soil springs to the structural engineers so that they could model the superstructure with a flexible base. So that goes back to what we were discussing previously. I understand that the engineers who worked on this worked very closely with the structural engineers. There's sort of a back and forth between, designing with the foundation. They'd submit their results to the structural engineers. Based on what they received, they would create a design for the superstructure, but then maybe certain design changes or certain criteria needed to be altered, just to get closer to what they wanted. So, there was a very sort of open line of communication. And if you have, relationship with structural engineers where you need to submit certain results to them, the program, programs such as such as GTS can help you achieve those sort of, very easy to read results. And then as far as spring adjustments, so based on the structural engineers' sort of input or feedback, they were able to predict settlements for the pile loads and get all the results to match. So for example, settlements and pile loads, wall loads, from the structural engineers. So they had to rerun the foundation model and adjust the pile springs appropriately. So I'm not sure how many times they had to rerun the model, but I'm sure it was enough times just to ensure that the results from the structural engineers and the geotech engineers were sort of in line and that everybody was on the same page with what they were doing. So once again, if you have someone who's very sort of adept with finite element modeling, especially someone who can use the program, then you'll be able to sort of work at a very high level in terms of working with structural engineers, meeting project goals, and getting your project within sort of a range that's both economical and very reliable as well. So it takes some time to learn, but there are many great advantages to having someone who's adept at finite element modeling within your company. So final remarks for this project. The iterative process gives insight on the redistribution of column and wall loads. So naturally, when the structural engineers, when they have maybe certain design changes or they have certain criteria that needs to be met, they'll come back to you and they'll have certain design changes or they'll have certain criteria for you. And then you'll be able to sort of iteratively sort of fine-tune your design just to make sure that, or to ensure that it, sort of reaches the engineer or the architect's vision. And then the redistribution is more pronounced when the superstructure is stiff compared to the foundation. So, as this is something I guess Kostas would be able to discuss, I guess, more in detail. But if you have a superstructure that's very stiff compared to the foundation. So something we discussed previously was how the Power Raft foundation is sort of flexible. So the more stiff your superstructure is, you have to it sort of affects how sort of flexible your foundation is, which is something that I won't discuss into too great detail right now. But later when you're creating your finite element modeling, you're working with your structural engineer, you'll see how there's a very direct relationship between the stiffness of the superstructure and the redistribution of your wall loads. And the redistribution may necessitate stiffening of the foundation. So once again, depending upon just sort of the criteria or what you're working with, you may need to stiffen your foundation. That all goes back to the specific project scope. But that's something when you're doing the design, it's an iterative process, which is why using that particular model, the beam with the interface element is so key, because iterative, doing your redesigns becomes much easier when you have something like that. Okay, so actually I think we have maybe 5 more minutes. So for those of you who maybe need to leave earlier to go to meetings, definitely, I'll get the material over to you. But for those of you who can stay for 5 or 10 minutes, what I'd like to do now is just to share a quick, just a couple of samples of our sample projects here for both PY analysis and foundation or numerical modeling. So let me exit out of this real quick. And I'll show you just very quickly just a sample. So this is SoilWorks. We showed, I think, a slope stability analysis type project on SoilWorks last week. So this is the foundation module of SoilWorks. So this does conventional analysis for group pile foundations. So for those of you who are new to numerical modeling, this is essentially what the parameters you'd have to input. So let's go to ground material properties here. You have your material properties for weathered rock, alluvial layers, etc. So you have your unit weight, your saturated unit weight, and for PY analysis, you have your separated reaction, your skin friction, your bearing capacity. These are all things you need beforehand, when you create your model. And then also, you would need your structural properties, so just the types of piles we're doing, just the foundation, or excuse me, the diameter, as well as your material parameters, modulus plasticity, etc. So as far as the analysis itself, it's fairly simple. So for this particular project, I have two types of foundation types, a 3x5 as well as a 3x3. If I go to the analysis here, or go to the results section, here are what the results look like. So I have my horizontal displacement, my moment, my shear force, my ground reactions for each of my individual piles. I also have them for, there's another way I could look at them here. As you can see, I have a PY curve for each section here. And I can sort of check immediately or directly how each pile foundation compares to the other. So I can compare the maximum displacements, moments, etc. So in terms of creating a numerical model, it's fairly simple and it's fairly straightforward. And this is typically used, once again, for smaller scale type projects. So for those of you who are interested in adapting a numerical modeling program specifically for conventional analysis or PY analysis, just get feel free to contact me about learning more about SOLRIX. I know there's a couple of you already who are looking further into it. And I know I'm just sort of scratching the surface about PY analysis for SOLRIX here, but we can discuss it at further length individually. So I just wanted to give everyone an introduction to SOLRIX and how we can handle PY analysis. And then last, what I'll do is I'll share very briefly here just a 3D model done in GTSNX. So this is somewhat similar to Costas' project. It's on a much smaller scale, obviously. But here we have our finite element model. It's for an embankment, and there's a pile foundation here. Let me just skip to the results. Or actually, let me show you the properties that were used here. So as you can see, because we were doing this in a numerical model, the material properties are much more in depth. So we're using the Moore-Coulomb model. So here we have some of the properties we saw previously, but you also have properties for nonlinear behavior, and then also we have specific interface elements to model the soil structure interaction. So if you pull it up here, as you can see, it's just two main properties: the ultimate shear force and the shear stiffness modulus. But these are all things that need to be sort of modeled individually. So as you can see, there's pile elements, or there's pile properties, and then there's the interface properties. So what I'll do is I'll just fast forward to the results here, and I'll help you take a look at the construction staging. So as you can see, the construction staging here, it consists of 5 different stages. So first we start off with our initial conditions. Let's take a look at the displacements. So as you can see, at the very beginning, there's no displacement. It's all 0. This is what our project looks like. But in the second construction stage, here, total translation, as you can see, there's a certain amount of uplift when the excavation takes place. And let me put this in the underform shape. So as you can see, here's our first stage of excavation, and there's some uplift when we do it. And then, in the next stage, under structural arrangement, here we have our displacements again. So now we're sort of inputting a structure here. So what happens is there's going to be an excavation, and then a concrete block will be installed, and then finally piles will be installed as well. So as you can see, you can get all the forces or all the results that I sort of alluded to previously with Costas' project, with the Langen project here. But let's fast forward to our piles, because that's what I guess is most important to us. So here we have our last sort of portion for loading, or external loading. So our final stage. So let's go to, as you can see, pile forces here, or excuse me, beam element forces. And then what we want to do is we want to turn off all the meshing except for our piles. So here are our piles. And as you can see, we can zoom in, we can get our axial forces, we can get our shear forces, and we can get our bending moments for each of those individual piles because they've been modeled as line elements. Okay? And then also, if we turn on our gauging shell element, or excuse me, our base lab element, we can also get, so this isn't a pile raft foundation, this is just a pile cap, but I'd be able to get the results for that as well. So here it doesn't have any sort of translation. If if I open up one of my other ones, let's see. As you can see, I can get my displacement for my my pile cap. So this is just a very brief sort of summary or brief review of a sample project. Since we're low on time, I won't go into too much more detail, but just keep in mind that for larger scale projects or construction stage projects, you typically want to use a higher end program and do the model in 3D, such as this. So yeah, for those of you who want to learn more about how to use finite element modeling for your own projects, or want to give these programs a try to apply maybe what you learned into maybe one of your past or future projects, just let me know, and I can provide you with a trial version of either program, either SOLIDWORKS or GTS, depending on your needs, and I can get you started with the modeling and everything. Okay, but for now, this concludes session 2. Thank you to everyone who took the time to come today. I'll make sure that you get a copy of the recording as well as a copy of the PowerPoint so you can refer back to it. So next session will be March 26th, 3 p.m., so that's 2 weeks from now, and the topic will be shallow spread footing foundations, so designing with standard as well as finite element modeling methods. If you have any questions, feel free to contact me. My phone number and email address are listed as follows. And if you want to learn more about our company, you can just go to MidasUser.com. So thank you again for your time and attention. I really appreciate it. If you have any questions or comments, feel free to contact me, and I'll do my best to help you out. I hope you all found this presentation useful, and until next week, best of luck with everything.